Hello everyone, welcome to research webinars. Today we have a topic focusing on the design and performance of sustainable recycled barriers to prevent soil pollution. This presentation will be given by Dr. Mercedes Regadío. Let me quickly introduce about Dr. Mercedes. She did a PhD on Earth Science and Environment 2012, has mostly worked in 3 research groups from different countries, and she in the Department of Geology and Geochemistry at the University of Autónoma de Madrid in Spain during the period of 2007 and 2013. She worked on the structure and properties of earth materials related to the waste liners. In the Department of Chemistry at KU Leuven, Belgium, and during the 2014-2017, she worked on the reactions acting on earth and waste materials and their challenging chemical analysis. And in the Department of Civil and Structural Engineering, the University of Sheffield in UK, in 2018 and 2020, she works on the engineering principle to build high attenuation recycle anti-pollution barriers for waste deposits. This allowed her to acquire knowledge in different but correlated scientific disciplines, geology, chemistry, and environmental engineering. As you see, this is a very important, a combination of interdisciplinary type geology, chemistry, environmental engineering, which is important for the pollution-related issues. Parallel to her research, she lectured on related topics related to the bachelor's and master's students in Spain, in Germany, and UK. In addition, she has supervising 2 PhD students and technicians, 4 technician postgraduate student stays, and also the mentored postdoctoral fellow at the University of Manchester, and also a listed researcher at the University of Autónoma Madrid, and also the cooperated with the TU Delft. She has 40 conference communications, 80% international, and 54 published documents, which includes 21 journal reviewed articles. She has collaborated, published with 36 international researchers from more than 20 universities, research centers, and companies. She's also an associate editor with the honorarium of the Elsevier Limited and a topic editor of Minerals. Finally, she is highly committed to supporting science as a mentor of early stage researchers, jury member of scientific events, organizer of international conferences, as a regular reviewer of journals, and also the same science disseminator. She is actually engaged in 12 activities in the last 2 years. As you see, Dr. Mercedes is not only a researcher, she's promoting research, and also she actually engaged with the students, young researchers. I think it's very good to know about Dr. Mercedes. I welcome her to our program, and I'm sure that this presentation will be useful to all of you. Let me quickly introduce about TechnoBase. As you know, the research webinars is organized by TechnoBase. TechnoBase is based in Thailand, established in 2005. It is recognized as International Resource Center for Industries and Technologies. We organize, our services are global. We offer trade exhibitions, training and conferences, webinars, business networks, publications, talent search, knowledge test, consulting, and the business matching. We cover a broad range of segments. Of course, polymer is one of the main areas, but we also have energy, environment, chemical technology, engineering, water and membranes, filtration, and also advanced technologies. So our services are a combination of an education, business, and networking. So it's an integrated approach of we do educating and business and networking. When it comes to the webinars, what we are organizing, we have 4 types of webinars. One is a know-how webinar. It is purely an educational webinar. All the topics we offer is for the training purposes. We work with experts globally. We keep on adding new topics and covering a same level focus: polymer, non-polymer, energy, environment, and also the chemical technology. The research webinar is we have what we have today: research webinar promoting research. We have technology webinars, which is promoting the commercial technologies from the industries, from the suppliers, and to promote applications of those technologies. And we do have eminent personality webinars, which is basically it's a journey of the well-experienced and well-respected persons, which are talking, basically we're talking about the person who is in industry doing work for older than 70+ years old people, and we like to know their journey, their hard work and lessons they learned. So we have 4 types of webinars under the TechnoBiz: know-how, research webinar, technology webinar, and also the eminent personality webinar. Please do check these websites, which you may find useful, and some of the topics are all relevant to you. When it comes to just adding some more information on the research webinar, what is the objective of research? Basically, we want to promote the research development to the industry, government sector, or whoever you want to use. And also, we want to create opportunities between researchers and industries and government sector. And there are some, if there are some new technology, new developments, research development, innovations, we'd like to find a way, create a platform for the researchers to commercialize these research developments. And most importantly, we provide opportunity for young researchers to promote their work. And we are working with the universities or research organizations to organize events jointly together to support them as a partner to promote research. See, at the end of the day, research is a backbone for the development. All of what, like Dr. Mess says, they're providing solutions. They're creating a new product, sort of, So this is very important. But we are all interested in the research development, which are permitted to share in the public domain only, not for if you are contract research, we have no interest. That is that is for the contract. But mostly all our presentations which we offer through the research webinar are basically permitted to share in the public domain. Okay, that's briefly about it. I welcome you all to check our website research-webinars.com for our latest information on our activities. Okay, let's today's topic on the design and performance of sustainable recycled barriers to prevent soil pollution. I invite Dr. Mestis to make a presentation now. Let me ask her to share her screen. There we go.
Okay. So now I'm sharing my screen with all of you. So good morning, good afternoon, wherever you are. So let's start with this seminar about the design and the performance of sustainable recycled barriers to prevent soil pollution and also water pollution. So let's start by one slide about my organization where I am working. I'm working in the University Autónoma de Madrid, which is abbreviated as UAM. This is a public university with 8 faculties: the Faculty of Science, Faculty of Humanities, Faculty of Engineering, and data from the academic year to 2017-2018. This university has more than 30,000 students, from which 20,000 were female. It has 3,200 academics from a total staff of 4,200. And in that academic year, there were defended a total of 2,200 PhD theses. This university has 3 main pillars. It's one is intensive research with scholarship and programs for attractive postdoctoral researches. For example, I highlight one postdoctoral career training, which is within the CBIS, which the deadline is in October, in 2-3 weeks. And it's a good condition for doing your research in our institutions, quite similar as the European Marie Curie postdoctoral fellowships. The second pillar is the high quality of teaching. We have a lot of bachelor's and master's degrees, and also some international agreements with other universities, most of them within Europe, but also, for example, with the University of Boston. And the last is the social commitment through enhanced employment programs and scholarships for students. Within the ranking, this university in the QS World University ranking of this year is among the 200 best universities in the world, the 100 best universities in Europe, is the second best university in the country, in Spain, and the best university in Madrid. Specifically, I'm working in the Department of Geology and Geochemistry in the Faculty of Science. And now a little bit more about me. I am a researcher with several years of experience in reducing pollution and reducing waste. These are my main interest areas. Since in 2007, I started my PhD in the University Autónoma of Madrid, and I focus on the transport of pollutants and the landfills through the natural substrata underneath. Then in 2014, I moved to Belgium, to the University of KU-Leuven, where I studied the recovery of metals from industrial waste and how to measure these metals within a complex matrix. Then in 2018, I moved to the United Kingdom, where I studied the design of engineered recycled barriers in the University of Sheffield. And recently, I came back to the University Autónoma of Madrid. In total, I have been working in 8 different research centers, 3 of them as staff and 5 of them as visitor. I was a visitor in the DTU, the Technical University of Denmark, and also in the University of Texas with a group of sustainable landfilling and waste management. So let's go into the topic and let's see how much waste do we produce. So it is estimated that every year 2 billion tons per year of waste are produced globally. And this is expected to increase by 70% in the next years. So where all this waste go to? Most of the waste is disposed in some form of landfill, and up to 90% in low-income countries. And from this waste, 33% is openly dumped. This means that there is no control measures and there is no risk study. So there is no way to control what is happening there. And the problem is that the waste has some moisture and some liquid, which is called leachate. And this liquid is full of contaminants that can damage the environment and also the human health. This is a representation of what will happen. We have a lot of waste. We have the leachate that can percolate and pass through the soil and then can reach the groundwater. Groundwater is important because it's the largest source of water for our consumption. It's the water that we use for drinking, for washing, for all our uses. And can you guess what the main source of pollution of groundwater is? Specifically the waste. So what is this leachate like? So this is a smelly and dark colored liquid, and the composition varies along with time. That means that, for example, in newly deposited waste, in new landfills, the composition of the leachate is more acidic, it has more oxidizing species, a lot of organic matter, and a lot of ions dissolved on it. It is called acetogenic phase, acetogenic leachate. But in old landfills, when the waste has been deposited for more than 5 or more than 10 years, then the composition varies and it has a higher pH, it's more anaerobic, it has lower amounts of organic compounds and of solutes dissolved in it. In this case, we're talking about methanogenic leachate. And here you can see a table which makes average values of parameters measured in the leachate, and you can see the classification into new landfills, medium-age landfills, and old or mature landfills. So, for example, the first parameters is the pH, and we can see how the pH normally increases with the landfill age from 7 in new landfills until 7.7 in more mature landfills. We also see the ammonia here NH4+, and we can see also how the concentration, the average concentration in this leachate is decreasing from 2000 milligrams per liter until 600 milligrams per liter. So we can see how it varies the composition with time, but in general, always the leachates are a solution made of sodium chloride and bicarbonate with a lot of ammonium, potassium, and organic matter that is difficult to decompose. In the case of metals, we don't find a lot of metals, and if we find them, normally they are nickel and chromium at low concentrations. So what happened when we compare leachate with natural water, like water we can find in the rivers or in the groundwater? So the natural water has no ammonium, and the concentration of ions dissolved in the water is much lower. We are talking about 1 or 3 orders of magnitude lower. So we have a liquid with high concentrations of pollutants that can be released because of the waste. And our focus is on studying what happened with these pollutants, how do they transport, and where, how far do they reach, and if there is a kind of mechanism that can attenuate the moving of the pollutants. For that, I will talk to you about 2 kinds of studies. The first one are real scenarios, and the second one are experiments. In the real scenarios, we analyze samples in the field that were in contact with the problem, with the pollution, and then we study what happened. In the experiments, we have much more control. We do it in the lab, and we set up an experiment to know what is going to happen and try to predict what will happen if we apply the same conditions in a real case scenario. I use LF as an abbreviation for landfill. So let's start with this project. It was a project based on a real scenarios. And in this study, what we did is to choose 5 different landfills in Spain and to measure what happened in the soil, in the substratum that was below the waste. This was a very unique study because normally what you find in the literature are samples collected from around the pollution source, like nearby rivers or nearby soil, but it's difficult to find samples that are collected just under the waste and in direct contact with the source of pollution. So here we took these samples below the waste and we choose locations in the landfills that has no engineered liner, that the geology in the area was clay material, and these 5 different landfills, they have different characteristics between them. So they have different size, between 3 and 36 hectares. They receive different amount of waste, between 0.4 and 4 tons of waste per year per square meter. They were active receiving waste in different periods of time, from 9 to 24 years. And we drill between 2 and 3 boreholes per landfill. The waste layer that we drill also varied between 10 and 45 meters of waste, and then we recover the core, the soil column, and we recover between 3 and 5 meters of substratum. So here you can see some pictures on the right of how we drill and pass through the waste. And then in the middle, you can see the sample, the column of sample between 3 and 5 meters that we recover. Then in the lab, we cut these in different samples that were 10 different depths. Okay, so at the end, we have more than 130 samples, and we measure more than 30 parameters in these samples. We measure parameters regarding the mineralogy, which minerals do we have here, and between 30 and 75 of the minerals were clays. The dominant clays vary. Sometimes it was islite, smectite, or kielenite. And then we also have other kinds of minerals, like in some cases we have carbonates. But we also measured some properties of these materials. For example, the CEC. CEC means cation exchange capacity, and it is very important capacity in clay minerals. These minerals has a negative charge surface, which is negatively charged. That means that they will take and they will absorb cations and interact electrostatically with the cations. And if the solution around change the chemical composition, then the cations will be different, and again they will exchange with the new cations. We also measure the SSA, which means specific surface area, because it's related also with absorption capacity for the elements dissolved in the liquid. So the higher it is, the better for the absorption of elements like the pollutants. And then we also measure the chemistry in the pore water of these soil materials, of these minerals. Like, for example, the EC, which means electrical conductivity, which is a measure to know how much ions are dissolved in the solution. We also measure the WSOC, which is the water-soluble organic carbon, which measures the organic compounds dissolved in the pore water, in the leachate or liquid passing through the materials, and other chemicals like chloride, ammonium, these ions that will be indicators to know which is the composition of the liquid that is passing through these materials. So first of all, what we did was a statistical study to know which parameters are the most important to focus on. So we have a lot of samples and we measure a lot of variables. That means a lot of data. By applying this statistical procedure, which is called principal component analysis, we can have a summary and highlight which are the most important parameters to take into account. So at the end, we have only 7 principal components, and these 7 principal components explain more than 79% of the variation of the data. In the graph on the right, we can see 2 of these principal components, number 1 and number 2. And we can see the dots that are from the 5 landfills. We can see that some landfills are explained better because of the principal component 2, and others because of PC1, the principal component 1. This is because of the nature of the waste. So when the nature of the waste comes from industrial activities, then the most important parameters are determined by the parameters of sodium, electrical conductivity, chloride, and water-soluble inorganic carbon, the PC1. On the other side, when the waste comes from houses, like municipal waste, then the most important parameters that will determine the pollution front are the ammonium, the alkalinity, the potassium, and the water-soluble organic carbon. So now let's go into how far does the pollution travel through the soil. And for that, we are talking about how much decrease the concentration of some substances dissolved in the leachate through the soil. Here we have 2 graphs, 2 figures. The one in the left represents the inorganic solutes, the inorganic ions dissolved in the water. EC is the electrical conductivity. And the second graph on the right represents the organic compounds dissolved in the liquid. So these 2 parameters will give us information about if they are very, very high, then we have the pollutants going there. If they are low concentration, low values, so the water that we have there is natural water, background values. The x-axis is the proportion of these parameters. So it's increasing towards the right and decreasing towards the left. The y-axis is the depth. How many meters are we into the material? So we can see the different lines that they represent different boreholes of different landfills. We can see the same pattern, that in the most shallow samples, we have higher values of EC and organic carbon. The leachate is there, but when we go down, then these values are decreasing with depth and they are reaching background values. So there is no effect of the pollutants dissolved in the leachate. So with this, we can summarize that the concentration of inorganic ions decreased a lot between 1.5 and 2.2 meters. And the concentration of organic compounds also decreased a lot in shorter distances. This will help us to evaluate in situ clays as geological barriers. Here we have different legislations, and we normally apply the European Union Directive of Landfills. This directive regarding landfills, it says that it applies the multi-barrier concept, which means that whenever building a landfills, there has to be successive barriers of protection. So there is a geological barrier, which is made of the natural material there. Then there is engineered barriers. Then there is control measures to take, etc. So in this case, we can evaluate the geological barrier by how much it will attenuate in 1 meter thickness. So now, this graph on the left is the same as I showed you before for electrical conductivity for the inorganic compounds dissolved in the liquid. And here I just want you to remember that the data, the lines we see there, the data come from 5 different landfills and 2 boreholes in each landfill. If you remember, these 5 landfills were not the same one. They have differences. Some of them were operating for 10 years. Some of them were operating for 20 years. Some of them receive 1 ton per year per square meter of waste. Another receive 10 times more of waste. So in this case, we try, if we want to compare the attenuation capacity of the different substrata, we also need to try to take into account these differences between the waste that they receive. So for that, we use this kind of index, the AC, the diffuse flux attenuation capacity index, which takes into account 3 main parameters. The first one is the ratio decrease per meter depth of the parameter under consideration, for example, of the electrical conductivity, EC. Then we also have to take into account the number of years of waste that it was being deposited there, because more waste means more leachate, and also the area. I mean, if the quantity of waste that was deposited there in which area, a big one or a small one. And that will help us to compare the results from different places instead of only focus on the different geology. So we have seen already that these materials, they are attenuating and stopping the transport of pollutants more than 2 meters below, but which processes are happening there? This is an example about sulfate concentration and the soluble organic carbon concentration. So we have this graph, also it is a depth profile, so how these two compounds vary with depth, and we see that they behave in opposite direction. So in the most shallow samples, the samples that are more in contact with the leachate, we have high content of organic compounds, which is normal because of the leachate, but low content of sulfate. This is because we are consuming, there are some microorganisms that are consuming sulfate to be able to eat the organic compounds and produce energy. So the organic compounds react with the sulfate and then they can produce energy. If we go down, then again we have sulfate and there is no organic matter, so there is no impact of the leachate and there is no reaction between them. The graph on the right is a pH diagram. This graph can be done for any metal, any cation, and it represents the most stable phase of that element regarding the value of pH and the value of redox potential. For example, here we have the different phases in which iron can be present, depending on the value of pH and redox potential. So if we go to the left side, when we have high pH, then the element iron mostly will be dissolved as an iron 2+ or iron 3+. But if we go to the right side of the graph, where the pH is higher, then the iron will be mostly precipitated as mineral phases, hydroxide mineral phases. This is something common between metals like nickel or chromium. When the pH is more than 8 or 9, these metals will precipitate as mineral phases and will be not mobile and will be immobilized in the form. So at the end, we came up with some guidelines about which are good conditions for having a geological barrier. And this is a high percentage of silicates or clay minerals, more than 45%. Also, the presence of carbonate minerals between 3 and 20%. This is because these minerals like calcite or dolomite buffer the pH, so they keep the pH basic, which is good for the precipitation and retention of metals. And regarding the transport through these barriers, we have the main transport is diffusion, so it's a chemical transport, because the movement of the water is very, very low, is lower than 10 to the power of -9 meters per square meters per second. We have some chemical processes that will help to retain the pollutants, like redox processes, dissolution and precipitation of minerals, and also the cation exchange. This property that I tell you before, that has some clay minerals, that they have their surface negatively charged, and because of that, they can attract the cations in the solution. If the solution changes, because, for example, it arrives at leachate, then these cations can be exchanged by the new cations that arrive, because now they are predominant in the solution. And what happened if we want to build a landfill in a place where the geological conditions are not proper for it? Then we have to add a geological barrier using a material that we know that it will work. And for that, we can do some experiments to test the different materials. So now we jump into the second type of studies, in which we do experiments at real scale or at another scale which is extrapolable, which can be simulate the reality, to know what will happen. So this experiment is to test how a barrier made of clay will interact with different leachate. So we use one clay with a high content of clay minerals, of silicates, more than 50%, also with carbonate minerals, and it was the pore water naturally has sulfate and calcium. This clay was put in contact with 4 different solutions. One was water, the other 2 was synthetic leachate, and then the black liquid was a real leachate for a landfill. So we put the clay in contact with 4 different liquids. We wait for 4 years, and after 4 years, we opened the columns and we took samples at different depths, similar to the real scenarios. And these are some attenuation depths of the main ions that dissolve in the leachate. This graph is again a depth profile. So in the y-axis, from top to bottom, are samples. In the top, samples that are in contact with the surface, with the leachate, and on the bottom is the deepest samples. And we can see on the x-axis the concentration of soluble ions or exchangeable cations on the line below. We can see again that ammonium is the main characteristic pollutant, and it has very high values in the columns with the leachate. And we can see how it dropped drastically in the first centimeters. Here we see shorter attenuation depths that when we studied the real cases in the landfills, mainly because of the time. Here we live 4 years in contact, leachate with the material. Meanwhile, before in the landfills, the waste was in contact with the soil for 10 or 24 years. And then we did a multivariate analysis of variance with all the data, because we wanted to know which parameters show a significant difference between the column with the real leachate and the other columns. And it resulted that the SSA, the specific surface area, decreased a lot in the case of the column with the real leachate, which is the green line here. So these samples on the top are samples in contact with the leachate, and as we go down are samples, deeper samples. And the x-axis is the value of the specific surface area that increases towards the right. These points here are the specific surface area in the columns without the real leachate, and we can see that it is more or less around this value. But in the case with the leachate, this value has decreased a lot. So why is this happening here? For that, we have to know how are the minerals of the clay in the material. So in the case of clays, that they have layers, they grow with layers, parallel layers between the layers, they have some space. This space is filled with the cations that neutralize the surface of the clay, and these cations are calcium and magnesium. In natural conditions, they are with calcium and magnesium. These cations have 2 charges, and they are strong enough to attract water molecules. So at the same time that between the layers of clays we have the cations, we have also 2 lines of water. This is in natural conditions. When we have landfill leachate, the solution and the solution changes. So the solution has a lot of ammonium and potassium. If we put in contact the previous clay with a solution full of ammonium and potassium, then the cations are exchange, because now the predominant cations are others. When we change the cations by ammonium and potassium, these cations are not, they cannot attract so much water, so there is less space between the layers of the minerals, so the minerals start to collapse, and the surface area is decreasing. So this effect can be also quantified with the depth profiles, because we measure the quantity of the cations in each sample at different depths. So on this left graph are the data from different landfills, and we can see how when we go down, it is decreasing the number of cations that are typically in the leachate, which are the ones that take less water with them when they exchange with the cations in the clay. And on the right side is the same effect, but with data from the experiment, the 4 columns of the clay with the leachate. So we can see also how at the shallow samples is when we have the biggest amount of the cations that will create this collapse in the structure of the minerals. And here I represent some isotherms with also on the left side with data from the real experiments, and on the right side with data from the columns test. This is an example for ammonium, because ammonium is the main characteristic pollutant in the leachate. And this, what measures is the affinity of the material to absorb and attract this ammonium. So we can see how the fitting is quite good, and if we calculate the partition coefficient, it's quite high, between 14 and 7 and 16. That means that most of the ammonium will go to the solid phase instead of staying in the liquid, in the mobile phase. So what does it mean? Is that if the ammonium stays in the solid, then it moves slow. It will move slower than the water, than the liquid. And this can be measured by a factor which is called the retardation factor. And this is a formula. You only need some the density, the porosity, the velocity of the water, and then you can take the retardation of the different cations. In this case, I show the cations that predominant, the ones that predominant in the leachate. These are potassium, sodium, and ammonium. And these are the retardation factor. That means that 52, 29, and 48 times they move these times lower than the velocity of the water. We are talking about very low velocities of the pollutants in the order of 10 to the power of minus 12 meters per second. This is very important. This shows you the high absorption capacity that these materials have for these cationic pollutants, so they can be retained in the soil for longer periods of time, and they can undergo attenuation. So again, this graph about the main effect of the leachate, where when we have no contamination, then we have a natural clay, hydrated clay with a lot of space and surface area. But when the leachate arrives, there is a change in the composition of the pore water, which exchange the cations, and then there is a collapse in the structure of the material. The layers of materials go closer, and then we arrive with this can produce cracks. And this on the right is a photograph in the microscope where we can see some macroporosity, these big channels. And this is can be a problem because these channels can act as a highway for the pollutants to travel faster. But we have also seen that there is new precipitation of new mineral phases, in this case calcite. in the shallow sample. And this may be because of the release of bicarbonates, because of the degradation of the organic matter and the decrease of the calcium in the exchangeable sites of the clays, then it may be a super saturated solution which will precipitate as a mineral which is calcite. And it will be also decreasing the porosity and these big channels that may act as a highway for the pollutants. So the next question is this enough for ensuring the safety in these landfill barriers that we want to create with the clay materials? And another question is, can we use other residues produced in industries in big quantities to improve the quality and the behavior of geological barriers? So we start from a point of seeing the advantages and disadvantages of using clay. Clays are good because of their high attenuation capacity. They are reacting with the pollutants, and they can absorb and attenuate the moving of the pollutants. They have very low permeability because they are reuse compacted, so the movement of water is very low. They support a lot of biological activity. They support a lot of microorganisms that can biodegrade the organic pollutants. But the problem with clays is that they can swell and shrink because of differences in the water, and this can cause channels through which the pollutants can escape. Then we think about reusing residues for mixing with clays, because residues are free. We focus in two of them, in aggregates from demolition and construction waste, and as from biomass power plants. These residues are free of cost. They are produced in big quantities. They have some absorption properties. They don't swell or shrink, but they have high permeability, which is not desirable for the barrier. So the idea is, why not try a combination of both materials together? For that, we need to do two things. The first one is to check that the residues, in this case aggregates from waste, from construction and demolition waste, and as from power plants, are safe to use. That means that if we use them, they are not going to release new pollutants to the environment. And the second one, once that we know that which residue to use because they are safe, we want to assess, to evaluate how the barrier will perform over a long period of time, over a period of time long enough for ensuring the safety of the disposal. For that, our experimental setup will be more dynamic. So it's not standing for years in columns. We will use a geotechnical centrifuge and some rules that will help us to extrapolate the results to real values in the real conditions. So let me explain here. So we will have columns. In the picture on the left, we see these cells, 12 cells that will have the material inside, and this big reservoir has the leachate inside. So this will be the experimental setup. The column is smaller than before, and we will be running also the experiment not for 4 years as before, but for some weeks. And we will accelerate it because of the spinning of the centrifuge. This setup is on the top of the basket of a huge geotechnical centrifuge, which is a spinning device, and it will spin like in this video. What does this allow us? So if we look into one of the cells, the image on the left, what we have in each of the cells is on the bottom, empty space to collect the water that goes down. Then in the middle, we have a column of 10 centimeters of the material we want to test its behavior as a landfill barrier. And on the top, we have 5 centimeters of the landfill leachate or rainwater, because we are going to percolate first landfill leachate and then the rainwater. And this is a model from the reality on the right. In the reality, we have a force of 1 gravity. And if we increase that force, then we can accelerate the experiment and we can use a smaller size of the sample. When we start spinning the centrifuge, we are increasing the gravity, and by applying some rules, we know that at this speed of 25 gravities, with a radius of 2 meters, 8 weeks spinning is equivalent to 100 years in the prototype, which is the real case, and 5 and 10 centimeters of the thickness of the barrier and head of the leachate is equivalent to 1.2 meters and 2.5 meters respectively. So the idea is to model the reality using the geotechnical centrifuge, so we can apply an experiment of weeks using centimeters of samples and then extrapolate the results to the scale of 100 years and meters of the barrier. So again, a figure about the experimental setup, in which in the basket we have the columns of the different barriers. We have a reservoir with the liquid, the leachate or the rainfall, and then we also have a connection and input of gas, which is a mixture of CO2 and nitrogen, because we want also to have a representative atmosphere with no oxygen, as in a real case. So which materials did we use? So we use clays that come from the United Kingdom. There are 3 main different clays with different characteristics. Coal measures clays, they were acidic and they have an intermediate plasticity, while Oxford and London clay, the ones that I will show some results, they have a very, very high plasticity or high plasticity in the case of Oxford clay. They have the best properties for attenuating the contaminants because of the proportion of smectite and halite minerals, also the high cation exchange capacity, and also because of carbonates that will buffer the pH. On the right, I saw the residues that we use to mix with these clays. One is the biomass biomass that comes from power plants. They have high porosity, low density, high pH, and high soluble salts. And we also use aggregates that comes from construction and demolition waste. They are very similar to the coal measures clays. So they are fine materials similar to natural fine sands and clays. They are basic and they contain sulfate. So first we apply leaching tests. Leaching tests, they are standards and they may vary from one location, one country to another country, but they are necessary to do for assessing the mobility of the pollutants in the material. They provide you information about if the material can be risked to use or not. We applied two different kinds of leaching tests. The first one was the rotation batch test that we perform in one stage and in cumulative states. That means that only one stage is at one liquid to solid ratio, and cumulative stage you add more water in a second stage. Basically, this test is you have a container, you put your material, you put water in a high liquid to solid ratio. Normally, you put 10 times more water than material, and then you rotate for a few hours or one day. After that, you stop, you take the liquid, the water, you filter, and you analyze the concentration of the elements in that water. The second test that we performed was the percolation test following this European standard. In this case, you fill the container with the material until the top. It's not compacted, but you fill the container. And then the water, you pass the water through in and out. You continuously flow the water through the material. And then you collect at different time intervals. You collect the water going out, and then that water you measure and you analyze the composition of that water. So when we analyze the composition of the water, all the elements were below the maximum limits for considering the waste as inert. So the waste were non-hazardous to use because of the release of the elements were below the maximum, the thresholds established. So now we have the green light for using these residues, and we are going to make mixtures. Between 5, 10, 20% of the material will be a residue, and the rest will be the clay that has the most highest capacity to absorb the contaminants, but also they have this problem of can swell a lot and shrink and then produce cracks. So we put the mixtures in the platform, in the basket of the centrifuge. We connect all the cables for the leachate or the rainwater, and also for the anaerobic gas. We spin for several weeks. After that, we take samples also at different depths, and then we can extrapolate the results to meters, in reality, meters of the barrier, and also 2 years, how many years was in contact. And here we have this graph, so don't worry, I will go through it. On the top and bottom x-axis is the same, is the time of the test. On the top is the test time, so it's the days that the centrifuge was spinning, and on the bottom is the equivalent when we talk about reality time, so it's the prototype time. So how many years was in contact when we want to know what will happen in reality. And here we have the fluid front, so the movement of the fluid through the barrier. So at this point, the fluid was at 0.4 meters. At this point, it goes down and down. And the different colors are different composition of the barrier. So from red is 20% of additive, green is 10%, and blue is around 5%. So as expected, we see a continuous flow, more or less constant flow, that goes down with time. Okay, so it goes faster when we have less clay and more additive, also as expected because of the characteristic of the material. The next we are going to see is what is the composition of this fluid front. Is it full of contaminants or not? What happened in the variation of the composition? So if we look at the organic compounds, the TOC is the total organic compound in the pore water. And we also represent a depth profile in our samples. Here I put two graphs because they are two different clays with 30% of addition of the aggregate. So we see how the organic compounds decrease with depth. And if we compare these values of organic compound in the barrier with the value in the leachate, which is in blue, 2000 milligrams per liter, we see a decrease until almost zero with the depth. Okay. Again, on the left side, we have the depth in the sample, and on the right side is the depth of the prototype in reality. So we can see how we decrease a lot in the first meter of the barrier. The next indicator of the landfill pollution is the ammonium. Here again we have two graphs, again for the two different clays, but these clays were mixed with 30% of the aggregate. And we see again how the concentration of ammonia decreased with depth. The blue line, the blue dotted line, is the value of ammonium in the leachate. In all cases, is high. And we can see how after 33 years of prototype, the ammonium did not reach the bottom of did not pass through the barrier. And then we also check the permeability constant or the hydraulic conductivity. That means how fast is the fluid flowing through our barrier. We wanted to check if there were some cracks or rapid movements or something that will break our barrier. So this graph, what does it mean? Here we have again the time. On the x-axis we have the time in years on the bottom or in test days on the top. And here on the y-axis we have the permeability. The dotted red line is the maximum limit value that the barriers should have to accomplish the European legislation, which is maximum 10 to the power of -9 meters per second. And then we have a vertical line here, the black vertical line. This only means that the liquid changed. So to model the first 33 years, we were permeating through the materials leachate, landfill leachate. After the 33 year, we started to permeate rainwater. So we can see again the different colors means different compositions. Red 20% of the additive, green 10%, and blue it was 5%. We can see that most of the time we are below the maximum limit, so it is okay. And just to finish about this new experimental setup with the geotechnical centrifuge, these graphs represent the depth profiles of the pH with different clays and different addition of the residue. The three lines are replicates. Two of them are within the same spinning, and the blue one line is in another spinning another day. So we can see that there is good reproducibility. We have very similar data, even though we change the color, even though between two replicates with the same spinning or another one with another spinning. So just to summarize this seminar, our research came because of a problem. the problem of the waste, that we generate a high quantity of waste, and this quantity is increasing. It doesn't seem to decrease. And that the managed option is still the most used option, is still dumped, especially in low-income countries. And this has several consequences, like the damage to environments and also to human health. What we propose is we try to find new cheap landfill barriers. We want to prove their performance in the long term. At the same time, we want to save a natural resource such as clay or soil. And at the same time, if we can, we also would like to recycle residues that are safe for using in this new application, and then they will not end up in a landfill. So thank you very much for your attention. If you have any questions, you can contact me through ResearchGate, in Twitter, or by email. You have here my address. And in case you are interested and want to deep more in these topics, I can also refer you to have a look to some of the publications. So in the real scenarios where we work with landfills, we have published in Waste Management and in the Journal of Science of the Total Environment. In the case of the experiments, we have some proceeding and also some work last year that was published in the Tritos. So again, thank you very much for your attention, and please contact me for any questions or comments that you may have.
Thank you very much, Dr. Mercedes. Guys, that's the end of the presentation. I'm hoping that you find it useful. Okay, on behalf of the research webinars, I thank you for joining this program today. Dr. Mercedes, thank you all. Thank you very much for supporting and presenting an interesting topic for the research webinars. Thank you very much.
Thank you. Bye.